Let's start with a question that has puzzled humanity for centuries. What is reality? Is it merely what we perceive with our senses, or is there a hidden, unseen layer to it? The reality we comprehend is largely defined by our sensory abilities. Our eyes discern light, our ears sounds, our skin senses touch. This sensory data assimilates in our brain to create an understandable depiction of the world around us. Yet what if I suggested that this depiction isn't the full narrative? Ponder upon this. There exist phenomena in the cosmos that our senses fail to perceive, such as the cosmic microwave background radiation remnants of the Big Bang, or the faint gravitational tug from far-off stars. These unseen forces sculpt our reality in ways we are only starting to understand. So, is our sensory perception of reality comprehensive, or are there concealed facets yet to be explored? Today we embark on an intellectual journey into an experiment that questions our fundamental perception of reality, the Wheeler's delayed choice experiment. Before we delve into the enigma of the Wheeler's delayed choice experiment, let's take a detour into the strange and fascinating world of quantum mechanics. This branch of physics that deals with the universe's minutest particles, like atoms and subatomic entities such as electrons and photons, is a realm that's bizarre and counterintuitive, defying the rules of classical physics. Let's kick off with a cornerstone of quantum mechanics, wave-particle duality. This idea posits that every particle also dons the cloak of a wave. Think of it as your beloved superhero with a covert persona, a humble particle by day, transforming into a wave teeming with potential by night. Consider light, for instance. Light can exhibit the characteristics of both a particle and a wave. We term these particle-like entities of light as photons. Photons are like minuscule bundles of light, ferrying energy from one location to another. On the other hand, light can also mimic a wave, dispersing and interfering with itself, generating patterns of brightness and darkness. Now here's where the quantum realm takes a turn for the utterly bizarre. Quantum mechanics proposes that particles exist in a state of superposition until they are observed. Superposition infers that a particle can occupy multiple locations simultaneously. It's only when we measure or observe a particle that it collapses into a definitive state. This phenomenon, known as the observer effect, ranks among the most mind-bending facets of quantum mechanics. You may find yourself wondering, that's absurd. How can something exist in two places at once? And you wouldn't be the first. Even Einstein harbored reservations, famously expressing, God does not play dice with the universe. Nevertheless, experimental evidence tells another tale, and the results have been reiterated over and over. Now that we've on the initial exploration of quantum mechanics, we're all set to dive into the enthralling narrative of the Wheeler's delayed choice experiment. Now, let's dive into the heart of the mystery, the Wheeler's delayed choice experiment. This experiment, suggested by physicist John Wheeler, takes us on a thrilling ride into the realm of quantum mechanics, where the traditional rules of physics seem to be disregarded. Let's decode the experiment in a simpler way. Visualize a light particle, a photon, emitted from a source, advancing towards a gadget known as a beam splitter. This gadget can either permit the photon to pass through directly, or it can reflect the photon at a right angle. Following the beam splitter, the photon meets two mirrors that reflect the photon towards two detectors. The twist here is that the experimenter can decide to position a second beam splitter in front of the detectors once the photon has already crossed the first beam splitter. This second beam splitter can merge the paths of the photon, inducing it to act like a wave and produce an interference pattern. Now, here's where things become really intriguing. If the second beam splitter is put in place, the photon behaves as if it was a wave from the instant it left the source. But if the second beam splitter is absent, photon behaves as if it was a particle from the beginning. This is the core of the Wheeler's delayed choice experiment. This may not seem surprising at first. However, the decision to include or exclude the second beam splitter is made after the photon has already moved past the first beam splitter. This indicates that the photon should have already settled on its status as a particle or a wave. But it seems the photon makes this decision based on future events. This experiment questions our traditional understanding of cause and effect. It's as if the photon aware of what the experimenter will do in advance, or as if the experimenter's choice is influencing the photon's behavior retroactively, Of course, this does not suggest that we can send messages to the past or foresee the future. It's more about how the nature of reality at the quantum level is interconnected in ways that we don't fully comprehend yet. What's captivating is that this isn't just a theoretical experiment. It's been carried out in reality, with results that support these peculiar predictions. In these experiments, photons, electrons, and even larger molecules have exhibited this extraordinary behavior, showcasing wave-like or particle-like traits based on decisions made after they've been emitted. So what does this imply? It proposes that the nature of reality at the quantum level may be affected by how we choose to observe it. It's a concept that continues to baffle scientists and philosophers alike. The end-to-end results of this experiment propose that the way we observe reality can influence the nature of reality itself. The results of the Wheeler's delayed choice experiment are nothing short of shocking. Going beyond just a mere scientific experiment, it serves as a doorway to an entirely novel understanding of reality. It throws down the gauntlet to our comprehension of the cosmos and our role within it, provoking us to question our ingrained beliefs about time, space, and causality. Central to these shocking revelations is the possibility that reality might not be as concrete as we previously believed. It could, in fact, be more of a fluid, changeable existence, molded by our observations. This idea greatly deviates from the classical physics perspective, where the universe functions like a finely tuned apparatus, independent of the observer. Take a moment to ponder the implications of such a fluid reality. It implies that the universe isn't merely out there, unfolding without our input. Instead, it suggests that our observations, our exchanges with the universe, play a part in sculpting reality. This doesn't mean that we can simply desire $1 million and have it spontaneously materialize. It's not about manipulating reality to cater to our whims. It's about the inherent essence of the universe at the quantum level, where particles exist in numerous states at once until they're observed. It's about the peculiar and fantastic realm of quantum mechanics, where the act of observing can affect that which is observed. The Wheeler's delayed choice experiment additionally thrusts us into grappling with the concept of retrocausality, the idea that the present can influence the past. This is a concept that defies our comprehension of linear time, comparable to reading the last chapter of a novel and somehow altering the beginning. Lastly, the experiment raises queries about the intrinsic nature of light. Is light a wave, a particle, or both? And how does our observation alter its behavior? This experiment paves the way for a myriad of possibilities and inquiries regarding the nature of our universe. It's a captivating expedition into the essence of quantum mechanics, a journey that persistently challenges, baffles, and inspires us.